Great. So we've now heard from Ian and Alan on 3D modeling tools that are available out there to geologists and geophysicists and how you would use them to your advantage in your exploration projects. We're now going to hear some case examples where 3D modeling has helped advance discoveries or has been used to find successful discoveries. Our next speaker is Bruce McMonnies. Bruce has successfully crossed the boundaries between geology, geophysics, geochemistry, and caused outstanding results for various commodities like diamonds, gold, base metals, coal, through project management and data integration. Bruce graduated from RMIT with a degree of a Bachelor of Applied Science in Geology in 1982. Bruce commenced working in a similar economic downturn as exists today. Bruce fell into geophysics working with TGDG, Seismic, and potential fields. In 1987, he started with De Beers as a geologist. A career spanning 20 years was spent working in Australia for 8, Brazil 6, and Canada 6. Bruce completed a Master's in Mineral Exploration Technologies in 1996 from Curtin University. He was the first person to receive this degree. From 2001, Bruce was responsible for all geophysics in America for De Beers. In 2007, Bruce started with Rio Tinto, and in 2008, he started BEM Geoscience and entered the consulting world developing the concept of 3D geosolutions. Today, Bruce will share with us a multidisciplinary 3D data integration case study from Snow Lake, Chisel Basin. Please welcome Bruce McMonnies.
Okay, I'd just like to say thanks for having me here today, and we'll get straight in it. The talk is Multi-disciplinary 3D data integration project, and it was all done at the Chisel Basin. The presentation outline, I'm going to give some idea of the project background, the exploration goal, Hudbay's particular objectives, the building of the geological model, how we've got value out of physical rock properties, and also I note from where Alan talked about the physical rock properties and automatic optical televiewers and acoustic televiewers. And then what we tried to do with all this detailed information in trying to do cluster analysis on the physical rock properties and the geochemistry. Then we took all the geophysical information and we tried to constrain everything in 3D. And out of these inversions, we took the susceptibility, the density, we had ZTEM, Titan data, plus lots of borehole EM as well. After all that, then we decided to put all this information into like a workflow targeting, and the whole idea was to get much better understanding and quantitative targets, and so then I'll outline what was actually achieved and the conclusions and acknowledgements. So the project background, Hudbay has been successfully exploring lots of mine in the Snow Lake Greenstone Belt, and they've been exploring for the last 50 years. 75% of the discoveries are basically attributed to geophysics, and it's primarily EM. So the whole idea is we try and find conductors. They've all been, initially they were airborne conductors, then those conductors were then chased on the ground to get a drill target. And then we've drilled to try and hit that conductor, and these drill holes have had borehole EM to find whether we've got an in-hole or off-hole conductor and whether we drill again. At the same time, they've got lots of geoscientific data, and it was never really put together. Numerous guys had tried there, nobody had the time. Again, the issues that Alan talked about, different datums, different projections, everything is quite it's just unused, and just individual data sets are left hanging and not really interpreted well, and nothing was really integrated. So the aim of the approach was to leverage all this information, and at the end of the day to target and try and find new sulfide mineralization with lower associated risk. And the tipping point for Hudbay was actually finding somebody that could run with this and actually produce something. They had many people tried in the past and they'd all failed. So there was a lack of wanting to do it until the right person came along. Okay, so the picture on the screen is exactly how the body is represented in all the literature. So it's all the different lenses of the different sulfides there for the Layla deposit and all the drill paths. And as you can see, there's no geology, no other information. It's just sits like that. And that's basically where the project starts. So the exploration goal was to develop the integration project and basically to understand everything and put all the knowledge together compared to the other known deposits in the Chisel Basin, and using all this information from the regional scale to target new prospective EMS deposits within the Chisel Basin. So the size of the model is the picture shown. The extent is rather a size. It's 100 square kilometres of the surface, and it's 3 kilometres deep. So when you take your 3D cells at 50 by 50 by 25 metres of depth, we have close to 5 million cells in the model. Okay, so the diagram shows. Where's the pointer on this? Red one. Okay, so this is our 100 square kilometres. We're looking at the geological map. That's good. How do we go back? Yeah, but I kept my fingers. Okay, so the concentration is all the drill holes we have in the project. So this is showing over Photo Lake. The Layla Lake deposit is sitting here, and these are our Chisel and Chisel North mines. So all our drilling is concentrated on where we have our mines, and this is the holes that were over the Layla deposit over here. So we have concentration of where the drilling has occurred and lots of area where we don't have anything.
Is that hole still?
Yes, in total there's more than 6,000 drill holes, and all the underground holes were also included. So in the model there's 6,000 drill holes. So the aim of the approach was to get a quantitative data integration project, and as I said, what we had was the ore solids and assay results. We had loads of geophysical surveys, and then all the things in red there, like the geological model, the alteration, the geochemistry, physical rock properties, spatial relationship, and constraint inversions. None of that was completed before I was involved. So the whole idea of this is to put it all together, one repository of all the information, and we want to get enhanced understanding and better targets at the end of the day. So the model construction started with a classic explicit method of cross sections and faults and trying to create the subsurface geology. And we had some problems because the surface geology wasn't automatically easy to push straight down to our horizon. We needed the person that was involved mainly was a guy called Al Bales from Manitoba Minerals and Mines, and he was brought back in to relook at holes and relook at and build all our cross sections. And because we wanted to take the geology that exists totally on board, we wanted his input to work with us that we weren't doing anything as a black box. So we took time, but we made sure we did it correctly with the information that we had. The other data set over the basin at this time was there was a single 2D seismic line. And what we're looking at here is a cross-section each side of the, looking into the page and out of the page, and where the drill holes marked, including the underground holes, were just stepped off like a maximum of 200 metres from the profile. And if you look on the, where the ore bodies are shown on the right, okay, they line up favourably and fitting different reflectors on the seismic profile. But if I didn't know where the ore bodies were, I'd have a lot of trouble trying to interpret it. But we could incorporate all this data. Before I was involved, this line was done. It was not even processed. It just sat there as in the two hard basket. Okay, so went back to the GSC who did this line, and pulled it out, migrated this data to what you see there, so we could incorporate everything that we had. And this slide shows the maximise the value from physical rock properties. What we were trying to do was we were just trying to get more out of the rock properties, really understand them, use these exact measurements, to work out, to have real values, to be able to constrain our inversions and all that, to be able to match up with our geology. So in looking at this, we, to improve the workflow and increase the speed and accuracy, there were 17 holes that were collected with physical rock properties or wireline properties. So the 17 holes, the measurements downhole were 20 centimetres, and then we had optical and acoustic televiewer measured 2 millimetres apart. Okay, so why did we do this? Well, we wanted the accuracy, and we wanted to check that the method is robust, and so we're getting the same readings all the time. So everything was calibrated and referenced. The parameters measured are all noted there. We had natural gamma, resistivity, fluid resistivity, spontaneous self-potential, magnetic susceptibility, inductive conductivity, neutron, temperature, density focused, sonic velocity, and the televiewers, the calipers, and also IP. So we measured everything we could possibly measure, and then we wanted to then be able to interpret this quantitative information. Just to look down hole on a cross section through our ore bodies of the Layla deposit. Now we can see this is magnetic susceptibility, and now we have this button is good. Now we can actually see that we have a lot of magnetic susceptibility in the hanging wall up the hole, but we also see that the magnetic susceptibility is also lining up pretty nicely with our zinc-rich unit at the which is covering our stack of ore bodies of the BMS deposit. If we look at density, and now the accuracy of the density shows that this zinc-rich ore body at the top is much higher in density, and we've got really good correlation. The small areas up the top are actually the wedges in the hole. That's how accurate the density measurements are. So we've got a great correlation of density with our ore bodies. If we look at conductance, which is what we've always been chasing, again, we have this great correlation with ore bodies. Okay, Alan mentioned about this in-situ orientation for optical and acoustic televiewers, and what we're really keen on is we've got the complete picture of the hole, and we get the true orientation. We can actually see our mineralization in the hole. We can see whether it's massive. We can see where it's disseminated. The left is the optical. The right is the acoustic. The acoustic is basically measuring like the hardness and softness. What that gives you is, when you look at that information in conjunction, we can get all the information of all our geotechnical information as well. So we see all the things like open fractures, whether they're closed fractures. The optical gives us more of the geology. We can directly link what we see to our physical rock properties. And as Alan said, all your errors are worked out in bringing in the information. So everything is basically verified and validated in the process of importing all the data. Okay, and in GoCAD we can display the features, the orientation. We can get contacts, veins, everything. When we take all our physical rock information, so here's all our parameters in profile down the hole. Okay, so this is the density, and the blue is susceptibility. And then when we look at geostatistically manipulating this information, that's touchy. We can see the original geology in the left column of the geology, and then in the next two columns is our cluster analysis. And we can do this cluster analysis because basically we've got about 6,000 points down each drill hole that goes down. And so we have all our assay results here corresponding with our conductance and all of our ore bodies and our sequence. What I wanted to point out from that slide is that we're getting, in automatically clustering them, we're getting great correlation between the contacts of our geology, which is our log geology. So what we wanted to do, we had this information, and then we also had, so this column shows my geology. This is, right corner. The second column was an amalgamation from our bales trying to combine holes to link everything up, and now we can see from that second column that we've pushed our limits too far with what we can see. We're making misinterpretations and combining the wrong units with the right unit. And then the next two columns is the physical rock properties. The first one, you can see, if I look at that, this unit here, and the same unit here, we're not getting any input out of the magnetic susceptibility. So when we rerun this unit to this rhyolitic unit, now we can see where this unit is magnetic and also where it's non-magnetic. Why do we want to know this? We want to know this because when we do any of these inversions, we're modeling a value over a set distance. Okay? So if I take an average of that unit and take those physical rock properties from being non-magnetic to really highly magnetic, I'm just getting a totally false value that I'm going to put over the wrong distance. So in effect, I'm dividing that unit into two, what's magnetic, what's non-magnetic. I can put a zero value to the non-magnetic part, and I can put a true magnetic value for the high magnetic part over that interval, and we can move on. If I compare it to the information, so you want to compare the first, third, and fourth column compared to my first column, and then we'll look at all the geochemistry values, and what do we see in the clustering of that. In the geochemistry, we have a sample every 30 metres down hole. Okay? So at 30 metres down the hole, these are the values. So the yellow is all my felsic rocks. The blue is my basaltic rocks, and you can see the correlation. All my detail is in my in the physical rock properties, but because I've got geochemistry for every drill hole, I can now extrapolate to the rest of my drill holes with confidence that I'm seeing the right things. And now you can see when we tried to force the geology, we couldn't do it, and we're missing things. Okay? But from the original geology to what we've done in this automatic cluster analysis compared to the geochemistry, we've had some very nice results. When we took all the drill holes over Lawler and over this deposit, we have a lithology code. Now what we had to do was that when we looked at this lithology code initially, there was 70 different names there. And just by eye, we put things together to shortcut the process. We wanted to simplify it. And we were quite logical in what we put together. But if you look at the cluster analysis on the right, now we can see how it's divided into 5 zones. So here the greens are the light greens are the basalt, the blues are my rhyolitic rock, the yellow is what we call this Icelandite or this enriched basalt, and the mineralization is in red. It really simplifies where we could start to draw boundaries in 3D and we see it in a different way. When we took all the data that they had, including surface samples, and we did the same thing, again we had 6 different clusters. So this really simplified it. If I look at in section to how we've drawn the geology, we didn't really fit everything too well in how these things cluster. And we can see gross faults and where they are in this data going downhole. But what's really interesting is that my powder house formation, which is in green, okay, here we always thought that this formation was in the footwall, and here we've got the same unit sitting at surface, which they didn't know. So it was all a way of reviewing the data and changing their whole thinking. What do they think of it? Well, they didn't think much of it because they weren't willing to change their ideas straight away, but that's the story. Okay. Okay. So what we want is, I'll use the word true as well, just to unnerve Jerry. We want something that's real. What's something that we see in geology that's real, and that's what we actually want to model. Okay. And there's been plenty of people that have talked about 3D data and 3D geological models, and it's always been a sound exploration strategy. What we've done here is it's quantitative information that we're taking. These are real values that we're trying to change and put into the equation. And once you do that, and if you put that into your workflow really early, you get the benefit of the information without these misconceptions of just guessing. Where we went with the clustering, the physical rock properties, these domains can provide an immediate interpretation product to the geologist. When we get into the footwall deposit, they can't distinguish what is actually, they can't actually see what is there, okay? But this is a robust, unbiased, and automatically our geological model is better when we're starting with IST information than just taking the geology as it's good. So incorporating this process has the potential to significantly improve quality, changes what you want to do, and we can make better decisions quicker. And overall, this can actually reduce exploration costs instead of adding to them. Okay, now we'll talk about a little bit about inversion. What is inversion in the forward modelling? Basically, as Ian said earlier, we're estimating the model of a physical rock property distribution, and that's based on that survey area, and the forward modelling is just the reverse of that. And when we do these models, we're just trying to minimise the error and going back and forth. So inversion directly transforms the geophysical data into physical rock property distributions that may be interpreted geologically. Inversion process needs the input from both the geological and geophysical data and create as output one or more geological models that are consistent with both types of data. Constrained inversion modifies a given physical rock property distribution such that it will be consistent with the geophysical data set. The value added is only as good as our understanding and expectation of physical rock property relationships in the relevant geological setting. So what I'm trying to say here is we need more constrained inversions. They're getting us to the real situation. And Hudbay made the decision to carry out 3D inversions of all their geophysical data sets. So the 3D geophysical inversions, we have ZTEM, we had the Titan MT, the Titan DCIP, we had the squids from Dennis Woods. Our mag and density data were modelled with BPMG, and we had 67 boreholes over Lawler, and with 35 channels and late time data over Lawler. So the idea is we want to actually understand, get better targets. If we look at the picture on the left, we're looking from the top down over our two big ground conductors, and where we've drilled. So you can see how that northern conductor is coincident with Layla. If we look at it from the bottom up, we can see the inversion of the ZTEM data. And yeah, it's not altogether perfect, but it's a bit like sausages. But what is interesting is that it's a fairly good fit to our two original anomalies. It's interesting that Lawler actually sits outside the shell of the inversion, so it's not perfect, but it's a good start. That jog in the ZTEM data, what was interesting about that jog is it's exactly coincident with the jog in the intrusive rock there. And So nothing's quite coincident, but it was a good starting point looking at ZTEM data. Now we'll jump to the borehole EM, and comparing to our coloured lenses of our ore body, we get where we've got control over this data, we've got ridges and runnels. So it's not this perfect picture that is displayed by how the deposit's been ore modelled. It's far more complicated where the actual conductance runs. The borehole inversion is in brown. The green is the MT, and the grey is the squid inversion. So now we can see underneath all this, there's a big section of the squid inversion that's seeing something much greater and much bigger at depth. What's this relate to? And if we combine that, we see these are just put together spatially, so you can see how the different shells, and we've put values on those shells, we've made statements on them, but the different from independent data sets are giving us the same picture, putting extra conductance exactly where we want it, so now we can see exactly where we want to drill or retest these things or focus our testing where these data sets spatially are overlapping. So now you can see that we have the DCIP data from Titan is coincident with the anomaly at depth. Just as we zoom in and look at these shells, we've got control. The red is where we have mineralization, and it's all coincident and lines up exactly where we've got our shell. If we compare that to our alteration, and we look at, again, our inversions, we get a pretty good concentration, and this deep anomaly is totally coincident with all the alteration. If we take some of our Titan data and we look at where the anomalies are, this is looking just as an extension from the chisel ore bodies over where the seismic is. We've got a big anomaly there that remains untested. Okay, so there's only surface shallow testing there. If we look over across to Frodo, again, there's another big untested anomaly that's still got to be tested. Okay, we went to we now go into this workflow targeting. We tried to take out exploration criteria, geology, structural, geochemistry, and geophysics, put it all together. We wanted to get the mineral potential modelling volume. Our main data sets were our susceptibility, our gravity, and ZTEM, which had the greater coverage. And we used the other data sets. What was the modelling approach was weights of evidence, training sets with different types of mineralisation for Lawler, Chisel, and Photo. The outputs were the probabilities with standard deviation, and our valid data sets was all our other information, such as the seismic, Titan, our ground data, everything else that we had. When we tried to generate targets with all the different parameters, we generated nice targets. We looked at our alteration, distance to the Plutons, all our alteration data as well. And then at the end of the day, we generated 22 targets. We had 10 conductive targets, 6 non-conductive targets, and there were 6 non-conductive targets at Chisel. Okay. So at the end of the day, GoCAD, what we want to say is what has been achieved. GoCAD provides a repository for all the data collected within the model limits. The seismic line was migrated and successfully imported. Our cluster analysis of the physical rock properties in lithogeochem showed we have 6 primary rock types. Inconsistencies with our current geological model need to be resolved. The electrical property 3D inversions were completed for each available data set. Each inversion validates, supports, and complements each other. The borehole EM inversion provided the most detail, and the 3D volume showing the conductance associated with the mapped ore lenses and shows where more conductive bodies exist away and still require further drill testing. The targeting workflow was built, generated, brownfields targets. There's It wasn't a perfect solution because we believe that it seemed to be over-dependent on the alteration and where we've drilled. At the end of the day, Hudbay have developed lots of GeoCat expertise. What I want to say, the model is alive. As you collect more data, the process is continuous and needs to be updated with new information. So they're working now on they've just completed a 3D seismic over the Chisel Basin. So in conclusions, like everybody else, geology is 3D. 3D geological models are simply much better using and honouring all the data. The model is the repository for all the data and validates the accuracy of the data. Geophysical survey data, physical rock properties, borehole logging data, lithogeochemistry, assays, structural control, and 3D constrained inversions are all fundamental tools required so that data can be visualized, interrogated, and understood in 3D. The geological model is alive and continually evolving. Changing the workflow generates a better understanding and new knowledge. Targets are unbiased and quantitative, using all of the available information. It is the fact that the earlier that you do this, there's far more benefits in leveraging all the information. Again, like the others have said, linking and connecting the current personnel to the big picture is the seamless approach, and everybody works for the same goals. And in Hudbay's case, they needed a champion to make it happen, and that's where we've got. So I'd just like to thank Hudbay, of course, all the guys at DGI, all the people at Mirror. There's a lot more than just me that did put all this together. I just coordinated lots of stuff. Yeah. I'd just like to read this last thing I've got here. The relationship between geology and geophysics has been discussed frequently. There can be little doubt, however, that geophysics and geology must cooperate to get a maximum of results. And this was written by Gutenberg in 1937. Thanks for your time.